All right, let's dive in. Today we're going to talk about something called the solid principles. Think of them as the 5 golden rules for writing software that's not just functional, but clean, strong, and actually built to last.
You know that feeling, right? Where you're looking at some code, and you just know that changing one little thing, one tiny line, could make the whole thing collapse like a house of cards. It's fragile, it's complex, and honestly, it's a huge headache for pretty much every developer at some point.
Well, guess what? There's a way to avoid that headache. They're called the solid principles, and they're basically a time-tested blueprint for building better software. They help us make systems that are just way easier to maintain, to change, and to understand.
So, what does SOLID actually stand for? Let's break this thing down letter by letter and see how each piece helps us build a much stronger foundation for our code. Okay, first up, we've got S. This stands for the single responsibility principle. But, I like to think of it as the specialist principle. It just makes more sense, and you'll see why in a second. It's all about focus.
So the official rule is, a class should have only one reason to change. Simple, right? But what does that actually mean? It means every single class, every little piece of your code should have one and only one job. When a class starts doing too many things, that's when it gets messy and becomes a magnet for bugs.
Let's put this in the real world. Imagine a baker. Their main job is to bake amazing bread. But what if they also had to manage all the inventory, and work the cash register, and clean the whole bakery at the end of the day? Their attention would be split everywhere, and the bread would definitely suffer.
And right there, that's the problem. And the solution. Instead of one person trying to do everything, a good bakery has a team, right? You've got the specialist baker, a cashier, an inventory manager. Each person has one job they're great at. And that is exactly what we want in our code. Separate classes, where each one is a specialist with a single, clear responsibility.
All right, next we're tackling O and L together. These two are a real power couple. They're all about how to let our code grow and add new features over time without breaking the stuff that's already working perfectly. It's absolutely critical for any project that needs to evolve.
O stands for the open/closed principle, and the idea is pretty cool. Your code should be open for extension, but closed for modification. So what on earth does that mean? It means you should always be able to add new functionality without going back and changing your old, stable code that you already know works.
Think about it like this. Say you have a payment system that takes credit cards. It works great. It's been tested. It's solid. Now your boss comes along and says, we need to accept PayPal. The open/closed principle says you shouldn't have to go in and change all that working credit card code. Nope. You just add a new module for PayPal. You extend what the system can do without risking what it already does.
Okay, now for L. This is the Liskov substitution principle. I know it sounds super academic and complicated, but the core idea is actually a really important check on that last principle. It basically says that if you create a new child class, you should be able to swap it in for its parent class, and the whole system shouldn't even notice. No errors, no weird behavior, nothing.
So let's play a little game. A square is a rectangle, right? I mean, in geometry class, it totally is. So it seems like it would make perfect sense to have a square class be a child of a rectangle class in our code. But is that really a good idea?
Well, in the world of code, this is actually a classic trap. It can cause total chaos. Think about it. You have some code that works with a rectangle. It sets the width to 10 and the height to 20. Now what happens if you feed it a square instead? A square has to have equal sides. So what does it do? This little logical mismatch breaks the substitution rule and creates these super subtle, really annoying bugs. It's a great reminder that real-world logic doesn't always translate one-to-one into code.
Okay, we're on the home stretch with I and D. These last two are all about how the different parts of our code talk to each other. It's about setting up clean, smart boundaries and contracts.
I is for the interface segregation principle. And the big idea here is simple. Don't force any class to deal with methods it doesn't even use. We want to avoid these huge bloated interfaces that try to be a one-stop shop for everything.
Here's another real-world analogy. Imagine you're a vegetarian and you go to a restaurant. The waiter hands you this giant leather-bound menu with pages and pages of steak, seafood, chicken, and then, tucked away in the back, is the one vegetarian option. You had to wade through all this irrelevant stuff just to find what you needed. It's just noise and makes things harder than they need to be.
So what's the better way? It's obvious, right? Separate menus, a vegetarian menu, a non-vegetarian menu, a drinks menu. In code, it's the exact same idea. We create smaller, more focused interfaces. That way, our classes only have to care about the menu that's actually relevant to them. It's just so much cleaner.
And that brings us to our last letter, D, for the dependency inversion principle. Now this one kind of flips traditional thinking upside down. It says our high-level, big-picture code shouldn't depend on the tiny, nitty-gritty implementation details. Instead, both the high-level and low-level stuff should depend on abstractions, like interfaces. This is kind of the secret sauce that holds it all together.
Think about how you use a tool like Git. As a developer, your high-level job is to write code. You rely on the idea, the abstraction, of version control. You know commands like commit, push, pull. You don't need to know the super complex details of how Git is storing all that data internally. You depend on the abstract idea, not the detailed implementation. And that separation is incredibly powerful and flexible.
So there you have it. SOLID, we've gone through all 5. But the big question is, why bother? What's the real payoff here? Why does this all matter so much?
Well, it's because these 5 principles aren't just a random checklist. When you use them together, they create a really powerful philosophy for how to design good software.
So what's the result? You get code that's way easier to maintain, because a change over here doesn't randomly break something way over there. You get systems that can actually scale because you can add new things without having to tear everything apart. And you get a flexible architecture that can actually adapt when business needs inevitably change. At the end of the day, the solid principles are really just about building with a better blueprint. It's about thinking beyond just, does it work right now, and instead creating software that's well-crafted, resilient, and truly designed to stand the test of time.
So I'll just leave you with this one question. The next time you sit down to code, ask yourself, am I just stacking blocks together to get the job done for today? Or am I actually building a solid, enduring architecture that my future self and my teammates will be thankful for?